Last time we were talking about electromagnetic radiation and radiation due to accelerated charges. So we were talking about this formula we introduced, and we were just playing around trying to get the directions correct for this radiative component to the electric field that is emitted by accelerated charges. So we have this formula, constant 1 over 4 pi epsilon 0 times a negative q perpendicular component of acceleration, that's a vector, divided by c squared r. And this is the magnitude of the r that points from the source to observation location, okay, which is also the direction of propagation of the emitted radiation. Okay. So, question? Oh, okay. Okay, so why don't we start with just a quick review of this and see if we can get some of these directions correct. So here's a question. We have a proton that is accelerated to the left, and we have various locations, A, B, C, D, and E. At which location will electromagnetic radiation not be detected? Okay, everywhere except number 5, direction or location E, right? Because that is it's along the line of the acceleration, right? So we said everywhere except along the line of acceleration, and that came out of well, from this formula we can see that, because if you have the acceleration in that direction and location E is here, and the first thing you do is you draw the r vector, which points from source to observation location, so that's r, and then you draw this perpendicular axis. Well, the acceleration there is no component along the perpendicular axis in that case, so you're not going to detect any radiation or radiative component to the electric field. You'll still have the Coulomb field. You'll still have the 1 over 4 pi epsilon 0 q over r squared field due to the presence of the charge, but you won't see this radiative component we talked about, that kink in the field line last time in the demonstration that we showed. That's only going to show up when you're on off axis, okay, off of that acceleration direction. Okay, no big problems there. Let's try this one. Proton is briefly accelerated in the direction showed. What's the direction of the radiative electric field that will be detected at location A? So now you have to go through the steps, apply this formula to figure out the direction, see what you get. Okay, so a little bit tougher on this one. Let's see if we can go through this. We have strong, okay, vote for 2. Well, 2 is the direction that points from the charge to the observation location, right? 2 is the direction of propagation, or the r vector, but that's not the direction of the electric field component that you would detect, right? The radiative electric field. That would be the direction of the Coulomb electric field. So we're talking about 4 or 8, and so the question is, how do we get the sign right? Well, let's look. We have charge accelerating that way, and here's the location. What was it? We'll call it A. And the first thing you do is draw R. Okay, so R points from source to observation location. All right, there's R. And then the next thing you do is draw the, what was it? Perpendicular. Okay, so the perpendicular axis is that way. So A perpendicular, the perpendicular component of the acceleration, is going to be in what direction? 8. Okay, so A perpendicular is in direction 8. And so after some time we wait and we find radiation that is going to be detected at location A, but remember it's negative Q times A perpendicular. So we have a negative sign times a positive charge, so the radiation we detect will be in direction 4. Okay, so E radiative will be that way. Okay? And again, it takes some time after the initial acceleration for that radiation to be detected, but once it gets there, it'll be in direction 4. Okay? Questions? Everybody okay? One more. Let's do one more. Okay, we have an electron now, and location A is right here. Electron's accelerated sort of up and to the right. What's the direction of the radiative electric field that will be detected at A? Okay, so direction 1 is going to be correct this time, right? Because the A perpendicular is also direction 1, right? If you decompose that. So why don't we get the sign flip this time? It's electron, right? So we have negative times a negative gives us a direction in the same direction. Okay. Okay, so we played around with the directions. Let's just try calculating it just to say we did it. So let's just do this example. We have an electron accelerating in that direction. So let's say the magnitude of the acceleration is pretty large. 2 times 10 to the 17th meters per second squared. Okay, now you might say that's a huge number. How is that possible? Well, electrons are light. Okay, they don't have a lot of mass, and so if you have an electric field, if you put an electron in the presence of an electric field, you can get a fairly large acceleration. And there's no limit to the size of acceleration. Okay, there is a limit to speed. You can't have a speed greater than the speed of light, but acceleration there's no upper limit on that, so we can have as large as one as we want. R is over here, or the location's over here. So let's say the distance R, magnitude of R is, let's make it 0.02 meters. Okay. And to find the perpendicular component of acceleration, we're going to need an angle here. And so let's say it's making a 20-degree angle with R. The acceleration makes a 20-degree angle with R. And this is an electron, so we know the charge. 10 to the minus 19. So what else do we need? We've got everything, right? We know the speed of light. The speed of light is 3 times 10 to the 8th. So plug it in. See if you can find, based on this, see if you can find the magnitude of the radiative component of the electric field when it in fact reaches location A. Remember, you need to use A perpendicular, so think about how you would calculate that. Six times 10 to the negative 25 volts per meter. Agree? Disagree? What do we get? Okay, what are you getting? 1.5 times 10 to the negative 7 volts per meter. Any other possibilities? Any other candidates? (1.5, 10 to the minus 7). Oh, what's one? 9 times 10 to the 9th. That's the one constant we needed, right? 9 times 10 to the 9th. Well, let's check it. Okay, let's check it. We have 9 times 10 to the 9th. And I have, well, I'm just looking for the magnitude here, so the sign's not going to matter. I have the magnitude of the charge. So that's 1.6 times 10 to the minus 19. How do I get A perpendicular? Sine of the angle, right? So I have 2 times 10 to the 17th times the sine of 20 degrees, divide by 3 times 10 to the 8th squared, and the distance we said is 0.02 meters. So what does that give you? Does that give you 1.5 times 10 to the minus 7? What is it? 17th? 5.47 times 10 to the minus 8 volts per meter. Are we converging on an answer now, or? Okay, all right, 5.4. So what was this one? Was this for getting the sine of 20? That was cosine of 20? Okay, so that was cosine 20. This was, I don't know, for getting the constant or something like that, right? But you want the perpendicular component of this, right? So it's got to be the opposite side of that angle, okay? So that's a sine. All right, everybody okay with this? Just for comparison, try calculating the Coulomb field. So what is the Coulomb field due to this charge at the same distance? Which you all should know that formula, right? I hope. Just the static electric field, the field due to just a static charge. Same distance, same charge. What's the formula? What's the formula? Come on, you know it. Come on, this is the very first thing you had to memorize. Q over R squared, 1 over 4 pi epsilon 0, Q over R squared. Okay? And then there's, R hat, but I don't just want the magnitude. Okay, so what's that? 3.6 times 10 to the negative 6. Okay? So which one's going to dominate? The Coulomb field. This is, 100 times bigger. So at this particular distance, the radiative field, even with this high acceleration, the radiative field is not going to make that big of a difference. But what you find is that what happens as you get farther and farther away. So for example, if I increase the distance here by a factor of 10, what would happen to the electric field, for the Coulomb electric field? It would go down by a factor of 100. If I increase the distance here by a factor of 10, what would happen? Go down by a factor of 10, right? Because the distance dependence is only 1 over r. So as you get farther and farther away, the radiative component will eventually start to dominate because it's going to decrease with distance at a much lower rate than the Coulomb field. So you'll have some homework with this, and you'll have to sort of compare and contrast the two, and in some cases you have to find the net field by adding the two together. But as you get farther away, the radiation field becomes much more important because it goes down with distance much less rapidly.